Okay, this is section 2.5 called Postulates and Paragraph Proofs. So to begin, we have a couple of definitions. A postulate, also known as an axiom, is a statement that is accepted as true without proof. Basic ideas about points, lines, and planes can be stated as postulates. So in this section, we're going to be taking a look at the point, line, and plane postulates. So, postulate 2.1. Through any 2 points, there is exactly one line. So in the example here, line N is the only line through points P and R. Postulate 2.2. Through any 3 non-collinear points, there is exactly one plane. Our example, plane K is the only plane through non-collinear points A, B, and C. Postulate 2.3. A line contains at least 2 points. Example, line N contains points P, Q, and R. Postulate 2.4. A plane contains at least 3 non-collinear points. Plane K contains non-collinear points L, B, C, and E. In postulate 2.5, if 2 points lie in a plane, then the entire line containing those points lies in the plane. Our example, points A and B lie in plane K, and line M contains points A and B, so line M is also in plane K. Now a little bit about intersections. So we have postulate 2.6. If 2 lines intersect, then their intersection is exactly 1 point. Example, lines S and T intersect at point P. In postulate 2.7, if 2 planes intersect, then their intersection is a line. Example, planes F and G intersect in line W. Now I'm on page 130, and I'm looking at problems 1 through 6. The directions say, explain how the figure illustrates that each statement is true. Then state the postulate that can be used to show each statement is true. So in number 1, planes P and Q intersect in line R. So in the solution it says identify planes P and Q and locate their intersection. So here's plane Q, here's plane P. And their intersection, the points in common would be this edge right here. And it says the left side and front side have a common edge line, R. Planes P and Q only intersect along line R. In other words, they don't intersect anywhere else. This plane would continue out in this direction, and this plane would continue out in this direction, but they only intersect along this edge. And then we have to give a postulate that can be used to show that this statement is always true, which would be postulate 2.7, which states that if 2 planes intersect, then their intersection is a line. Number 3 talks about line N contains points C, D, and E. So identify line N and locate the points on it. So here is line N, and the points on it are D, C, and E. The front bottom edge of the figure is line N, which contains points D, C, and E. So we need to give a postulate that shows that this statement is true, that line N contains points C, D, and E, which would be postulate 2.3, which states a line contains at least 2 points. Therefore, it will contain 3 points. If it needs to contain at least 2, then that means 2 or more. Number 5, line N lies in plane Q. So we need to identify plane Q and locate line N. Here's plane Q. Line N is this line. Points D and E which are on line N, lie in plane Q. So D and E are in this plane. So line N lies in plane Q. So we need a postulate that shows that this line will lie in this plane, since we know these 2 points lie in this plane. And that would be postulate 2.5, which states that if 2 points lie in a plane, then the entire line containing those points lies in that plane. In numbers 7 through 9, our directions are to determine whether each statement is always, sometimes, or never true, and to explain your reasoning. Number 7 says the intersection of 3 planes is a line. So in our solution it says if 3 planes intersect, then their intersection may be a line or a point. Postulate 2.7 states that 2 planes intersect, then their intersection is a line. So based off of this postulate, that would be good enough to show that this statement is sometimes true. It says the intersection of 3 planes is a line. So if you have 2 planes intersecting, their intersection is a line. Therefore, the statement is sometimes true. And we have some diagrams here to help show that. So in the first diagram, I have 3 planes intersecting, and their intersection, their points in common, would be this line. Below that, I have 3 planes intersecting, and this time their common point of intersection, point P, they would have point P in common, no other points in common. So either they intersect in a line like the first diagram, and for some reason that's not coming up again, sorry, or they can intersect at a common point. Number 9 says through any 2 points there is exactly 1 line. So this statement would always be true, and the way that we can explain it is by using a postulate. Notice that postulate 2.1 says exactly that. Through any 2 points there is exactly 1 line. So postulate 2.1 states that through any 2 points there's exactly 1 line, therefore the statement is always true. So when you go back to number 8, to show that it's sometimes, always, or never true, look at your postulates and base your answer off of what they say. On numbers 10 through 13, our directions say, in the figure, ray AK is in plane P, and point M is on line NE. State the postulate that can be used to show each statement is true. So, number 11 says line NE contains points N and M. So here's line NE, here are points N and M. So in the solution it says it is stated that M is on line NE. So that's in our directions. M is on NE. N is part of the name of line NE, so N must also be on line NE. So we now know that M and N are on this line. Postulate 2.3 states that a line contains at least 2 points. So line NE contains points N and M. So here, N and M are on line NE, therefore line NE contains the points N and M. So once again, really all you need to say is state the postulate that can be used to show it is true. So our answer would be postulate 2.3 states that a line contains at least 2 points. A line contains at least 2 points. 13. State a postulate to show that points N, K, and A are coplanar, or on the same plane. N, K, and A are 3 points in the figure. So let's see, N, K, and A. There they are. We did not know for sure that N is on plane P. No other relevant information is provided. Postulate 2.4 states that a plane contains at least 3 non-collinear points. Here, the points N, K, and A are on a plane, most likely plane P, so they are coplanar. So once again, the answer for this, the only thing that we have to give to show that this is true, is postulate 2.4, which states that a plane contains at least 3 non-collinear points. So now, if you're following along with this lesson, it would be time to try some problems on your own. So try page 130, 2 through 12, evens. Take about 5 minutes to work on these. Okay, for numbers 16 through 23, it says explain how the picture illustrates that each statement is true. Then state the postulate that can be used to show each statement is true. On number 17, planes P and Q intersect in line M. So the first thing we want to do is identify planes P and Q and locate line M. So plane P is here, plane Q is there, and line M is right there. The edges of the sides of the bottom layer of the cake intersect. Plane P and Q of this cake intersect only once in line M. So that would be the first part, explaining how the illustration, or the picture, how the picture illustrates that each statement is true, or that this statement is true. And then the next part, we want to give a postulate that helps prove that it's true. So postulate 2.7 states that if 2 planes intersect, then their intersection is a line. So for a problem like 17, first we want to explain based off the picture why it's true, and then also give a postulate which proves that it's true. Number 19 says point D is also on the line N through points C and K. So we want to identify line N, which is this line, and locate points D, C, and K, right there. It says the top edge of the bottom layer of the cake is a straight line N. Points C, D, and K lie along this edge, so they lie along line N. So that's the first part of our answer, showing how the picture illustrates what is being said here. So points C, D, and K lie along this edge, so they lie along N. The second part is we want to give a postulate proving that it's true, which is postulate 2.3, which states that a line contains at least 2 points. So in this case, there are 3 points, so it has to contain at least 2. Therefore, the truth that C, D, and K will all be on that line is verified. And number 21, it says points E, F, and G are coplanar or on the same plane. So locate points E, F, and G. E right here, F right here, and G right there. The bottom right part of the cake is a side. So this side right here. The side contains K, E, F, and G, which forms a plane. So K, E, F, and G forms a plane right there. Postulate 2.2 states that through any three non-collinear points, there is exactly one plane. So these points will all be on the same plane because through any three non-collinear points, there exists exactly one plane. Number 23, lines H and G intersect. So locate lines H and G, which are here and there, which they are in fact intersecting. The top edges of the bottom layer form intersecting lines. Lines H and G of this cake intersect only once at point J. The postulate that verifies this is postulate 2.6, which states that if two lines intersect, then their intersection is exactly one point. On 24 through 29, our directions are to determine whether each statement is always, sometimes, or never true, and to explain. So 25 states that there are at least three lines through points J and K. Our solution would be postulate 2.1, which states through any 2 points there is exactly one line, therefore the statement is never true. So through any 2 points there exists exactly one line. This is saying that there is at least 3 lines. So that's why it is never true. Number 27. Points X and Y are in plane Z. Any point collinear with X and Y is in plane Z as well. So any point on the same line with X and Y will also be in the plane. So the postulate that we would use here is postulate 2.5, which states if 2 points lie in a plane, then the entire line containing those points lies in that plane. Therefore, the statement is always true. In the figure below, points V, W, X, and Y are all on line N, which is in plane Z. So V, W, X, and Y are all on this line N, which is in this plane, plane Z. Any other point on line N will also be on plane Z, even if the point is clear out here, because remember that the plane would also extend past these boundaries right here. So the plane would also go through that point, the point that's out here. So once again, for our answer, we just need to state sometimes, always, or never. So in this case, since it's directly related to postulate 2.5, we would state postulate 2.5 and we would say that it is always true. Okay, so we have one more like this. Number 29, points A, B, and C determine a plane. Solution. The points must be non-collinear to determine a plane by postulate 2.2. Therefore, the statement is sometimes true. So the key word there is collinear or non-collinear. So we're just given 3 points. We don't know for sure if they're non-collinear. That's why it's sometimes true. So in this diagram, 3 non-collinear points determine a plane. That's postulate 2.2. 3 collinear points determine a line. Actually, through any 2 points, there exists exactly one line. So it only takes 2 points to determine a line. But in this case, if they're all on the same line, that does not determine a plane. The points have to be non-collinear to determine the plane. So right now, on page 131, go ahead and try 16 through 28 evens. Take about 5 minutes or so to work those out. So if we take a minute to go back to number 15, it says in the figure, segment AE is congruent to segment DB. So they are the same length. And C is the midpoint of AE and DB. So C splits the segment into two congruent segments. Write a paragraph proof that shows that AC is equal to CB. So the length here is equal to the length there. That's what we want to show based off of this information that we're given. So this takes us into a new realm of geometry called proof. So a couple of definitions here. First of all, to prove a conjecture, you use deductive reasoning to move from a hypothesis to the conclusion of the conjecture you are trying to prove. This is done by writing a proof, which is a logical argument in which each statement you make is supported by a statement that is accepted as true. And for a paragraph proof. So one method of proving statements and conjectures, a paragraph proof, involves writing a paragraph to explain why a conjecture for a given situation is true. So at this point, we're going to prove that AC is equal to CB based off of this information and any definitions, postulates, and theorems that we know. So you're given a midpoint and a pair of congruent segments, AE and DB. Use your knowledge of midpoints and congruent segments to obtain information about AC and CB, the segments that you're trying to prove congruent. So this is kind of the plan for the proof, and now we go into the proof itself. So since C is the midpoint of AE and DB, once again, that was stated up here, since we know that, then we can say that CA is equal to CE, because it's smack dab in the middle. And those are each going to equal 1/2 of the entire thing, so half of AE. Likewise, we can say that CD equals CB, which is half of the entire thing here, DB. And this is all by the definition of a midpoint. So we're giving a reason why we can say this, because that's what a midpoint does. That's what a midpoint is. It splits a segment into two congruent segments which are equal to half of the length of the entire segment. Then we go on in our proof. We're also given that AE is congruent to DB. Right there it says it. So if that's the case, we can say that the length of AE is equal to the length of DB by the definition of congruent segments. So the definition of congruent, once again, states that if two things are congruent, then they will be equal in length. So we're stating that they're equal in length because we know that they're congruent. And we go further in the proof. By the multiplication property, so this is a property from algebra, that if we take an equation, we can multiply both sides by the same thing. Then we get this equation, if we multiply both sides by 1/2. So by the multiplication property of equality, we can say that half of AE is equal to half of DB. And then we're going to substitute. Since we know that half of AE is equal to AC, and that was right up here, CA or AC equals CE equals half of AE. Since those all three equal each other, then we can interchange them. So I'm taking half of AE, and in its place, I'm putting AC. Also, half of DB is equal to CB, which was stated back here. So half of DB is equal to CB, so I can interchange them for each other. They mean the same thing. So if I do that, I'm putting AC in on this side and getting this. I'm putting CB in on this side and getting this. So I'm changing those two values out with these two values, and I'm getting what I wanted to prove. So once again, what I wanted to prove is that AC is equal to CB, so I went through all of those steps, and I finally arrived at my answer, that AC is equal to CB. So that's what a paragraph proof is. All right, number 31, we want to write a proof. Point L is the midpoint of JK. So you can see that on my diagram, these two segments are congruent. That's what those marks mean. JK intersects MK at point K. So JK and MK intersecting at point K. If MK is congruent to JL, so MK has the same mark as JL, we want to prove that LK is also congruent to MK, that JK and MK are congruent. So here's the plan for the proof. You're given a midpoint and a pair of intersecting segments, JK and MK. Use your knowledge of midpoint and congruent segments to obtain information about LK and MK, the segments that you're trying to prove congruent. So we state our given information. L is the midpoint of JK. JK intersects MK at point K, and MK is congruent to JL. Then we state what we want to prove. So we want to prove that LK and MK are congruent. So now we go into our proof. We always state some given information to begin. So we're given that L is the midpoint of JK and MK is congruent to JL. So that was stated right here. L is the midpoint and MK and JL are congruent. So now that we have that information established, we can say by the midpoint theorem that JL and LK are congruent. So JL and LK are congruent by the midpoint theorem, which states that if L is the midpoint of JK, then these two segments have to be congruent, which is what we just stated there. And then by the transitive property of equality, we can say that LK is congruent to MK. And the reason why the transitive property works here is transitive property would say that if A equals B and B equals C, then we can say that A is equal to C because A and C are both equal to B. So in this case, we start off with MK is congruent to JL. Okay, so MK is congruent to JL. And by the midpoint theorem, we showed that JL is congruent to LK. So since MK and LK are both congruent to JL, then by the transitive property, they have to be congruent to each other because they're congruent to the same thing. So that's how the transitive property works. And that's our proof. So that's what we wanted to show, was that LK and MK are congruent. So at this time, you have one proof in your assignment that you need to do, which is on page 131, and it is number 30. So on numbers 34 through 41, our directions say in the figure, line CD and CE lie in plane P, and line DH and DJ lie in plane Q. State the postulate that can be used to show each statement is true. So, for 35, which postulate shows that line EG contains points E, F, and G? So identify line EG. Here it is. Locate the points on the line. There they are. Postulate 2.3 states that a line contains at least 2 points. Therefore, points E, F, and G, 3 points, will lie on line EG. Number 37. So which postulate shows that D and F are collinear? So locate points D and F. There's D, there's F. Postulate 2.1 states that through any 2 points there's exactly one line. Therefore, you can draw a line through points D and F. So that would be postulate 2.1. So which postulate verifies that plane Q contains points C, H, D, and J? Identify plane Q, so that is this gold one here, and locate the points on it. So C, H, D, and J. Those are all points on that plane. Postulate 2.4 states that a plane contains at least 3 non-collinear points. So plane Q will contain these 4 points, C, H, D, and J, since it has to contain at least 3 non-collinear points. Then on to number 41. Plane P and Q intersect at line CD. Identify plane P and Q and locate line CD. So there's line CD, here's plane Q, here's plane P. So, in other words, what common points do they have? And that would be all the points on this line. So it goes on to say, postulate 2.7 states that if 2 planes intersect, then their intersection is in fact a line. Thus, line CD is the line of intersection of planes P and Q.